Okay? Now, whenever possible, you try to avoid slow reactions, right? But sometimes it's unavoidable. For example, a hypothetical situation that you know this reaction is slow, but there's no alternative. This is the reaction you must need to use. Okay, then you need to consider to use catalysts, right? Once you add catalyst, then you can speed up this reaction. So remember the definition for catalyst. You know, the catalyst, the function is to lower the activation energy, so the reaction is faster. Okay. So what it amounts to, the catalyst is going to, this is a redox reaction, right? So the catalyst must facilitate the electron transfer. Okay, so that is the key understanding for that. So once you add the catalyst, it facilitates electron transfer, then therefore the catalyst must function as a bridge to carry the electron moving from one to another. So that will lower the activation energy. Okay?
You need to get the slide.
Yeah, that's good.
Page about 16.
First of all, let's realize the slow reaction, the mechanism for the slow reactions. It turns out that there are intermediate reactions to slow down the overall reaction. So what it amounts to, when this react with a tin2 plus, then you're going to generate this, and that this is an intermediate chemical before you get to the final. So this is the final product. Okay, so initially it's a 2 plus. So the 2 plus need to change into 3 plus first. So you know this will be reduced, and this one is oxidized, and that is a slow process. Okay, the slow step. Once you get this generated, once you have that, then that will react with another 3 plus and end up to the final product. And this is fast. So now you combine the two reactions, right? And now you have this overall reaction. So this is the same as when you combine the two half reaction, and you're going to end up with this overall reaction. Okay? So this is a net reaction. So it looks like if you could take care of the slow reaction to generate the SN3 plus, then you will speed up the reaction. Okay, so the catalyst in this particular reaction is simply the chloride anion. Okay, so once you add chloride anion into the mixture, then the reaction rate is here to the concentration of chloride, exponent 4, the power 4, right? So there's a tremendous increase in the rate, right? So 10,000 times faster than the original rate. Okay, then how do you explain the increase? Then we look at. Yes.
Will the reaction rate change with bromine or iodine? Or will it be constant for all those halogens?
Well, you will have to run the experiment to see. But then I extrapolate that this is halogen, right?
Yeah.
Then you learn from freshman chemistry that they behave similarly. Then of course you put halogen in it, and it will have similar effect, similar. But there will be, when you look into detail, then there could be some difference because of, right, the higher the group, the lower the group, then you get different electronegativity, electron affinity kind of thing, right? And you can affect the rate that way.
So A does not equal B, nor does it equal C. Did you say for the halogen?
Once you get the basic idea, right, then you can go into the laboratory and do the experiment yourself and measure. Yeah.
If they
That's
don't-
right.
Then look at the mechanism, then you understand better, right? Yes,
What is the exponent 4 coming from?
there's an experimental result.
Oh, that.
Experimental results, that's what a catalyst is, to speed up the reaction rate. The rate is sped up by this magnitude, mathematically, okay? So, looking at the mechanism for Jeffrey, it turns out that 4 comes in like this. So you have 4 moles in front, and therefore concentration to the power of 4. Then what will be the combination, right? So it turns out that the chloride will make a bridge in between the tin 2 plus and the Fe3 plus, like that. So you have 4 chlorides. Okay, so the bridge will facilitate electron hopping. Okay, the electron will hop, while chlorides are electron rich, so they function as electron cloud bridge, so facilitate the electron move from the 2 plus to the 3 plus, right? Go like this, go like that. Okay, so you have the electron. So here is the 2 plus, the tin 2 plus. So the electron here, the cloud, the electron go away, and this becomes a tin 3 plus, right? So electron add to the 3 plus here, then becomes a 2 plus. So facilitate, this intermediate will facilitate the formation of these 2, right? So once you get that, then immediately you proceed to the product, right? So this is the rate limiting step, and it is greatly enhanced. So you can explain that, right? Jeffrey?
No.
Electron cloud, looking at that electron cloud, so you enhance the cloud. So the cloud is practically touching this cloud and that cloud, so the electron is going to go forward.
I don't believe in electrons.
Photon, right? Yeah,
I think it's something else that we just haven't discovered yet.
okay. Any question? So this drawing thing, if you have the abstractive mind, that you should practice your abstractive mind. Envision the electron dots as cloud, the cloud, that
I'm working.
mixed together now. So the cloud is in one cloud, so move faster within that cloud.
I'm working on it. It'll take me 50 years, but
Yeah,
I'm gonna keep on chopping
so
at that
funny.
tree, and it's gonna come down.
you're in a party, you must be a center of attention. Draw
You'd be like,
discussions
"Who's
and
coming in
debate.
here, Peter Bong?"
Yeah, I'm sure it's a lot of fun having you in the party. Yeah.
With the chlorine, so 4 chlorines take the electrons, 1 from iron and 3 from Sn.
Well, notice the intermediate involvement of the intermediate from there. So this is the drawing of the above, right? So the tin 2 plus, this is the tin 2 plus, has its own cloud surrounding it. Then the chloride is surrounding the tin 2 plus. Then there will be electron clouds surrounding, so it will become big cloud. So here, the Fe3 plus has its own cloud too, because now you have all the clouds practically connecting to each other. So now this is 3 plus, right? And then this is 2 plus, so there's an affinity for electrons, right? Because your redox reaction indicate that this guy is going to be reduced, right? And this one is going to be oxidized, right? So there will be a tendency for the electron to move in this direction, and now you have bridges available, so for the electron to hop faster, because that is spontaneous, right? So now is the rate is faster to achieve the spontaneous, right? So the catalyst is going to reduce the activation energy. And once you have that, then pretty fast, then you get this 2, right? So the electron transfer, then the 3 plus becomes a 2 plus. So now once you get this 2, then the next step from the previous slide, the next step is a fast one. So immediately to form the product, once you get that intermediate. Okay? Okay, so that's it. That's been fun.
So you know what I think I'm gonna do after I'm done with these biology and chemistry degree, Dr. Ames?
You're gonna teach.
I think I'm gonna move to a